Okay, so here we've got a problem where essentially we're going to look to prove that these two matrices are inverses, and that's really what the problem states. Prove that if A equals this and B equals this, then B is the inverse of A, and we got to make sure that we improve, because it's a proof, that we include all the necessary components. So what we're going to start off with is a let statement. Our let statement looks like this. Let A equal the matrix that's given above, so -3, 7, 6, 1, and B equal that matrix that's given above. So we're really just saying, hey, if this is the scenario and we want to create that scenario, then we can prove that these two things are inverses through our proof process. Alright, so there's your let statement. That's it. We're going to start with these two inverses. The next step is we know that if A times B equals the identity matrix, so when we go through and do matrix multiplication, if it equals the identity matrix, then B is the inverse of A. So this is what we're going to try to show. If A times B equals I, then we know that it's then we've proven that B is the inverse matrix, so or the inverse of A. So that's all we're really going to do, is we're going to say A times B. So then A times B equals -3, 7, 6, 1 times that matrix up there, -1/45. 7/45, 2/15, and 1/15. We're just going to go through and multiply like normal. So normal matrix multiplication. So we've got this row over here, -3 times 7. So that's -3 times -1/45 is going to give me +3/45. And we're going to add that to 7 times 2/15. So 7 times 2 is 14. So that's 14/15, and that's our entry in the top left. This row times this column is going to give us -21/45. We're going to add that to 7/15. That's our entry in the top right, and we'll simplify that later. Second row here, 6 times -1/45 is -6/45. We're going to add that to 1 times 2/15, so that's 2/15. And the next one is 6/1 times 7/45, so that's 42/45 times 1, or I'm sorry, plus 1 times 1/15, which we just know is 1/15. So go through and simplify. Up here, we got to get a common denominator, so we need to multiply this by 3. Well, 14/15 times 3/3 is going to give us 42/45. 42 plus our 3 is going to give us 45/45. So that's good. We get a 1 there. This guy, common denominator again, 7/15 times 3/3. It's going to give us 21/45. So we get a -21 and a +21, and that gives us a 0/45. Down here we've got -6, and again common denominator multiplied by 3, we'll get -6 and a +6, gives us 0/45. And then over here, multiply this by 3, we'll get 42 plus 3/45 gives us our 45/45. And we know that this is equal to 1001 when we simplify, and that's what we needed. We needed the identity matrix. So all of our proofs, as usual, all of our proofs are going to end with, we just showed that A times B equals I, and up here we said, all right, we know that if A times B equals I, then B's got to be the inverse. So that's what we're going to conclude with. So therefore, since we showed A times B equals I, then we know B must be the inverse of A. So this is a little different than the one you saw on your test. The one you saw on your test actually was not the inverse because it didn't work out, but it's the same premise here. If we can show that when we multiply the two matrices together we get the identity matrix, then they have to be inverses. If when we multiply them together you don't get the identity matrix, then we can conclude that they're not inverses.